All right. So welcome everyone to this week's Autonomy Talks. Actually, it's great. We're starting the new here with a new speaker. Today is a great pleasure to have with us Professor Eric Mazumdar, who is an assistant professor at California Institute of Technology, specifically in the computing and mathematical sciences. Something about Eric, he obtained a Bachelor of Science in ECS, actually here at MIT, and then moved to better weather to obtain his PhD at UC Berkeley in electrical engineering and computer science, working with Michael Jordan and Shankar Sastry. His research lies at the intersection of machine learning and economics, and he is broadly interested in developing tools and understanding necessary to confidently deploy machine learning algorithms into societal scale systems. As you have seen from the bio we have shared, he is the recipient of many awards, which is great. And today he's going to talk about economics-inspired machine learning. I have personally been following a lot of these efforts from he and his group, and I am very excited to hear more about it. Just a quick note, please feel free to share your questions in the chat during the talk. We will see if we're able to answer them on the go, and we will have a Q&A at the end as well. So without further ado, Eric, thanks again for coming, and the stage is yours.
Yeah, no, thank you for the invitation and thanks for having me. I'm looking forward to this. The usual spiel with these online talks, please interrupt with questions. It's always more fun if these are interactive. So yeah, today I'm going to talk on kind of this beginning line of work that me and my group are starting to embark on, which is really on economics-inspired machine learning. And, I like to start with an extremely high-level motivation, which is just very obvious to, I think, most of us on the call, which is that algorithms are increasingly making consequential decisions, right? They're being used to, choose whether or not to send people to jail or to give them bail. It's if you go to San Francisco, there are autonomous taxis actually driving around in the city, and some of them are getting in crashes, some of them are causing traffic, and so on. Algorithms are being used to give mortgages, right? And now AI is being used to see who to hire and who to interview for jobs. And I think this just goes to show that these technologies that are being developed are extremely powerful, and we would like to use them for decision making, for consequential decision making. But I think at the moment we just the real world is much more complicated and things go wrong, right? When algorithms are deployed into the real world, people have a tendency to respond to them strategically and try to manipulate them. So, again, there are just a bunch of examples on this slide. There's people on all of these dating platforms who try and manipulate the app to try and get, more dates. There's job applicants who, copy and paste the entire posting of a job into their CV so that it passes, all of the keyword checks. This is one of my favorite examples. This is from Didi, which is the Uber in China. And there was a study that was done that showed that some large number of Didi drivers, something around 30% of them, I think, had a secondary app that told them how to drive. Had a secondary app that actually tells them how to drive to maximize profit. Now, that secondary app is not affiliated with Didi itself, but it gathers a lot of information from these drivers about where they are and demand, and it kind of routes them to where the surge and the prices are high. And so if you think about it, this is exactly a multi-agent scenario between two apps, and so really interesting dynamics kind of emerge. And then you have kind of classic examples of people fighting back against traffic routing apps like Google Maps and things like this. And I think this is a very kind of natural outcome. I think we're only starting to see more and more of these as AI algorithms actually are deployed into the real world. But I think this becomes a real challenge for algorithm design because, in a sense, a lot of our algorithms are not meant to deal with these kind of strategic behaviors. So, this is one of my favorite examples that just makes this so clear. So this is a study that was done in the 1990s, and it was basically a program that was run to give people subsidies based off of what's known as a poverty index score. this poverty index score was calculated based off of kind of their self-reported income, self-reported features, basically. In 1994, when they came up with this program, this was the distribution of poverty index scores, and they thresholded it, at this red line here. And if you were below this red line, you'd get some subsidies, you get some money, and if you were above, you'd get nothing. And in 1997, they ran this program again, and it was kind of a similar, looking data distribution. And then in 1998, the explicit, algorithm for how these poverty index scores were calculated, and also the threshold was actually announced to, trying to be transparent. And you kind of see this really funny thing happen in the distribution that, as soon as people realize that they can manipulate and how to manipulate, they do. And so you see everyone on the right side of this threshold, misreports just a little bit to be able to get the subsidy. And by 2003, this metric that they've come up with is entirely useless because everyone's manipulating it. And so I just really like this example because it really shows, not only a form of distribution shift that we might be familiar with in machine learning, but it's a very kind of structured form of distribution shift. But it's also a very visual representation of Goodhart's law in economics, right? Which says that any metric that you might come up with is going to be gained. And so, dealing with situations like this is something that I think a lot of machine learning algorithms currently can't do. And that's, where a lot of my research kind of focuses on. So in particular, I think, I use this slide to kind of talk about what my overall research is. And so, we're increasingly interested in how machine learning algorithms are used in strategic environments. And, the environments that me and my group look at are situations in which decision-making algorithms make decisions in uncertain dynamic environments that are evolving over time. And these algorithms interact not just with other algorithms, but also with people. And so kind of making sense of this picture is kind of the core goal, I would say, of my group. And so I'll give you kind of an overview of some of the recent work that we've done in this area. So, these problems are, as I kind of alluded to, much more complicated than the normal machine learning, right? So, as soon as we have multi-agent interactions, we start seeing big problems in our current approach to machine learning. This is, some of my early work kind of at the end of my PhD, showing that if you just use, really simple reinforcement learning algorithms or just single agent reinforcement learning algorithms in multi-agent problems, you can get very kind of complex and strange behaviors. So, what's going to happen here is we just have players using policy gradient algorithms to do rock, paper, scissors. And what I'm showing on the right here in this video is just, the relative weight that one player is putting on paper, one player is putting on, the same player is putting on rock, and then the other player is putting on scissors. And basically what you see is that they converge to basically tracing out this torus in this three-dimensional space. And in 6 dimensions, it's even more complicated. But what's interesting about this is they will never converge. They will never actually repeat the same strategy exactly ever. And it's actually a form of very controlled chaos, as we know in dynamical systems theory. So even in kind of such a simple game like rock, paper, scissors, taking a simple reinforcement learning algorithm, we see chaos, right? And this, I think, just exhibits how hard these problems can be if we're not careful. In some other work that we did in kind of recent years, we showed that even really simple, design decisions that you might make in machine learning, like choosing your step size or choosing exactly what gradient estimator you might use, can actually give you vastly different equilibrium outcomes in games. So in fact, if you choose your step size too slow or choose your step size too fast, you can essentially change, you can actually change the order of play in the underlying game and actually use, just these really naive design decisions for equilibrium selection. And that's something that just, again, doesn't happen in normal optimization or normal single agent reinforcement learning. Maybe some more recent work, we've been trying to understand how we should go about choosing our policy classes or our model classes in strategic environments. And again, we found this kind of surprising, unintuitive behavior that in strategic settings, and in strategic classification or in multi-agent reinforcement learning, you could actually prove that sometimes it's better to choose smaller, less expressive model classes, even with infinite data and compute, because they give you better equilibrium performance at equilibrium. So on the left here, I'm just showing the Nash equilibrium payoff as I move from a less expressive policy class to a more expressive policy class. And what you can see is that your payoff kind of monotonically decreases as your policy class gets more and more expressive. So as you can kind of represent more complex policies. And again, this just highlights how games and strategic environments are just fundamentally different from single agent reinforcement learning or from single agent problems. And lastly, the last video I'll give you is just some work that we also have showing that, even really complex kind of state-of-the-art learning algorithms like LLMs can actually be perfectly manipulated by small coordinated groups of people. And so we have some work kind of showing how a small coordinated group of people that we call a coalition can make imperceptible changes to a little bit of their training data and create perfectly exploitable backdoors for a larger population. And so, these are real kind of issues even in this age of AI and so on. So, to get to the meat of my talk today, I'm going to kind of talk to you about economics-inspired machine learning algorithms. And I think the theme here is really just that we take ideas from economics and we use them as kind of structure for different, problems in machine learning. And I think the maybe not surprising, thing that comes out of this for a lot of control people is that adding structure just makes a lot of these machine learning problems more tractable, more interpretable, and so on. And so I'll go over kind of two different works in this kind of line of thinking. The first is basically multi-agent reinforcement learning, but if the reinforcement learning agents that we deploy have features of human decision-making from behavioral economics. And what we'll see is that this gives us kind of a principled foundation for multi-agent reinforcement learning. The second is going to be a line of work on distribution shift and especially strategic distribution shifts. So, just the first in the first part of the talk, I'll basically show you that by giving RL agents features of human decision making, we can make all general sum games efficiently solvable via decentralized learning. And in the second part of the talk, I'll basically show how simplistic models of distribution shift can lead us astray. And so if we bring in this more complex model that I'll propose, which uses Wasserstein gradient flows, we can actually get some really nice insights into how to deal with distribution shift in machine learning. Great. So I'll dive into this first part of the talk. And this is joint work with two of my postdocs at Caltech, so Kishan Panaganti and Lai Shi. So they're both on the job market this year. So hopefully you find this interesting. Great. So, the overarching question I think that led us to this problem was really thinking about how agents should learn in dynamic game theoretic settings, right? I've shown you that, if we just use really naive algorithms, you can get very complex behaviors. And basically non-stationarity that can arise out of the use of learning algorithms in games, and this can lead you to non-convergence and chaos and so on. And so, we might think about what we might want from our learning algorithms in game theoretic settings. We might want our algorithms to be convergent, meaning that they might converge to some sort of equilibrium, maybe a Nash equilibrium in some sense. They might converge in the last iterate and the best iterate on average. Ideally, we'd like our agents to be able to converge independently, so they shouldn't have to know anything about their opponent's utility function to converge. And somehow the solution that we get to should be individually rationalizable. It should kind of take advantage of naive opponents. And, if you're at a solution, you should be able to rationalize it without, coordination. So, the question that, in some sense, I think the emerging consensus in the field of learning in games is that this is almost too much to ask for general sum multi-agent reinforcement learning. There's kind of so many negative results, starting from, I'd say, the really famous work by Kostas Daskalakis and Christos Papadimitriou on just the fundamental hardness of computing Nash equilibria, all the way to more recent results on the hardness of equilibria in Markov games, the non-trivial dynamics that can come out of no-regret algorithms and something known as the curse of multi-agency, there's just a lot of negative results on the underlying equilibrium computation problem at the heart of multi-agent reinforcement learning and learning in games. Just saying that this problem is just fundamentally too hard. In large games, the scaling just depends exponentially on the size of the action spaces, on the number of players, and so on. And so, this, I think, made us worry that there maybe just is no principled approach to dealing with these problems. And so, we took a different tack in our work with Kishan and Laishi, which was basically to define. We were able to come up with a computationally tractable class of equilibria. So moving away from Nash equilibria. And this class of equilibria will exist in all normal form and finite horizon stochastic games. And it's going to be computationally tractable in a way that's independent of the underlying game structure. And as I'll show you, it actually captures a lot of human experiments that were done in behavioral economics. And the key idea is that we're going to bring in ideas from behavioral economics into these games, and we're going to say our agent are going to be risk averse, and risk averse in particular to the randomness introduced into the game by their opponents and the environment. And they're going to be boundedly rational. They're going to have a systematic failure to perfectly optimize. And by bringing in these two properties into games, we're going to, give rise to this general class of equilibria that we could compute in all games. And to me, this is kind of an exciting result because starting from this foundation now, we can then develop algorithms and things that have kind of solid foundations, which is something that to my knowledge has been kind of missing in multi-agent reinforcement learning so far. So let me just introduce some notation. So we're going to be operating in the realm of n-player finite action games just to start. So we're going to have n players. Each player is going to have a finite action space. And then each player wants to maximize their expected payoff over the space of mixed strategies, pi I, which is just the probability simplex across their pure strategies. So the utility for each player is just ui, which depends on their own action and the action of all the other players except for them, pi minus I. And it's going to be the expected value of their reward, r, I. So very kind of simple setup, very classic. If you think of that game, as I mentioned, the natural solution concept for individually rational agents is a Nash equilibrium. So a strategy is a Nash equilibrium, for those of you who aren't familiar with this. Its pi star is going to be Nash if no player has any incentive to unilaterally deviate. So what that means is that if we, fix all the other players to play pi star minus I, then you have no incentive to unilaterally deviate to another strategy, pi I over pi I star. Right? So this is kind of your classic definition of Nash. And as I mentioned, this is intractable to compute outside of highly structured games like zero-sum games or cooperative games. And the fact that it's intractable to compute has led the field to focus on other types of equilibria, like correlated equilibria, coarse correlated equilibria, and even some more recent things on kind of smooth Nash equilibria. But I would say that, a lot of these still have their big drawbacks. They're computationally tractable, but they might not be individually rationalizable. They might require some form of correlation to rationalize. And so you just have, and you have big problems of equilibrium selection in all of these problems as well. You might have multiple Nash equilibria and so on, or multiple correlated equilibria or so on. Another kind of downside I'd say to Nash is that there's a long history in behavioral economics that say that Nash equilibria is not at all predictive of what humans do in game theoretic situations, right? This is kind of the basis of all of behavioral economics, which just says that people fail to be rational in some sense. People fail to perfectly optimize. And so, there's a long line in behavioral economics also kind of moving away from Nash, proposing other types of equilibria. And so on. And so, we're going to take kind of inspiration from behavioral economics, and we'll, as I mentioned, introduce risk aversion and bounded rationality into these games. And this is kind of a nice connection with some classic work in behavioral economics, which shows that to actually recreate human behavior very well, especially in games, you actually need, both of these properties. Each of them individually doesn't actually capture human decision making very well in kind of laboratory settings. But if you use both of them, then you can actually recreate human play in experiments. And one of my colleagues here at Caltech, Tom Palfrey, has this really nice paper where they made people play a bunch of generalized matching pennies games in labs and just tried to, see what they would converge to. And what they found is that what they converged to is some form of a risk-averse solution with some form of bounded rationality, right? And I think this maps very well onto kind of classic findings in behavioral economics that people are risk-averse and people are boundedly rational. And this is kind of work that got Kahneman and Tversky the Nobel Prize. Great. So to introduce risk aversion into the games that we're going to look at, we're going to make use of a general class of convex risk metrics. So for those of you who aren't familiar, a convex risk metric is just a generalization of the expectation that satisfies monotonicity. So basically, if y is better than x, almost surely, then the risk associated with y should be less than the risk associated with x. It should satisfy translation invariance. So just if you add a constant, it should basically, come out of the expectation. And it should be kind of convex in this sense. So this is a general class of convex risk metrics. It captures entropic risks, value at risk, conditional value at risk, phi divergence-based risk measure, shortfall risks. Choose your favorite risk metric, and it probably falls into this regime. But let's try and just, introduce it into games. So we're going to assume that players, as I mentioned, are risk averse to their opponent's randomness, and also maybe even the randomness in the reward. But we'll just assume that it is deterministic for now, just to make things simple. And we'll also just choose an arbitrary convex risk metric. So this is our original game. Each player wants to maximize their own payoff. And then, what they'll do to introduce risk is they'll evaluate the risk associated with each of their pure strategies. So for each AI, we'll look at the risk associated with AI, under the opponent's mixed strategy pi minus I. And then given that, they'll just minimize their expected risk over their mixed strategy pi I. Right? And the key here is that players should somehow be indifferent among pure strategies that yield the same risk level, right? So a very kind of simple, introduction of risk. You just look at the risk associated with each of your actions, and then you just mix over those to find the action with the least risk. Any questions about that setup so far? Cool. So this, very simple paradigm reduces to very well studied risk-averse control and risk-averse RL paradigms in single agent settings. So, it is kind of well motivated. And we could also define this other kind of more conservative flavor of risk, which is just switching the order of the expectation and the risk metric. And we call this the aggregate risk. And just for the purposes of today, we'll kind of analyze it a little bit. So there's a question which is why risk is a function of reward. Yeah, so risk is a function of reward. Sorry, let me go back. So the goal of risk is that you'd like to trade off kind of higher variance, but more, higher reward strategies with lower variance, but potentially lower reward strategies. And so this risk metric basically allows you to trade off between that. So think of these risk metrics as basically capturing something about the variance of your reward and regularizing with that. So that's why risk has to depend on the magnitude of your reward in some sense. Did that answer the question? Cool. I'll hope it does. Oh, let me see. Yep. Yeah. So risk here really has to depend on the reward, because the goal of risk aversion is so that people can bias themselves towards lower variance, but and therefore kind of lower reward solutions. Um, and so and this kind of makes sense. People want, maybe they're willing to give up some of their reward for kind of more certainty in their outcomes. Um, and so there's just kind of this trade-off that's captured in this risk metric, and that's kind of what this allows us to do. Great. And we just have two forms of introducing risk. One is this action-dependent risk, and one is this more conservative one, which is this aggregate risk. For the purpose of today, I'll focus on the aggregate risk case just because the math is a little bit cleaner. But in the paper, we also have almost exactly the same results for the action-dependent risk case as well. Great. So, given that we've introduced risk into the problem, we can now define the natural solution concept when individuals are individually rational and risk averse. And that's what we call a risk averse Nash equilibrium. And a risk averse Nash equilibrium is exactly the same thing as a Nash equilibrium, just on this function Fi. No player should have any incentive to unilaterally deviate from this risk averse Nash equilibrium, basically. Great. So, we could ask very kind of simple questions when we define a new equilibrium concept. One is, does it exist? And two is, maybe can we compute it? So, on the case of existence, it's nice because we've used convex risk metrics. And so then what we can show is that a risk-averse Nash equilibrium will always exist in all games. And this is kind of an important place where we start to diverge from, I think, one of the only other papers that we've seen, tackle this problem of risk aversion in games from a theoretical standpoint. Basically, in this previous work by Amos Fiat and Christos Papadimitriou from 2010, they assumed that you were risk averse to all of the randomness in the game, including the randomness introduced by your own mix strategy. And if you do that, then a risk averse Nash equilibrium might not exist. But in our formulation, you are risk averse only to your opponent and the environment, not to your own randomness. And that allows you to have this kind of nice existence property. Great. So unfortunately, risk aversion isn't enough to guarantee that this equilibrium is computationally tractable. And as I mentioned, risk aversion alone is also not enough to ensure that this equilibrium is predictive of any kind of human behavior. There's some work in behavioral economics that kind of backs that up. And so to get computational tractability, we'll introduce bounded rationality. And bounded rationality is just introducing this idea that people basically have a systematic failure to optimize. And this is sometimes captured by this idea that they optimize over a smaller set of quanto response functions instead of best response functions. And so a quanto response function is just a continuous function, so that basically if that maps from Rn to the simplex, such that if x is greater than y, you put more weight on y than x. So there's again kind of a flipping of the sign there. And that's because we're minimizing. And so, all this does is it kind of smooths out the problem. So you're optimizing over a smaller set of strategies, over a smaller set of mixed strategies. And we're going from minimizing our function f over the simplex to minimizing our function f over the set of quantal best responses, which is a smaller set than the original simplex. And the nice thing is that you can actually write this as just a regularized form of the game. So you just introduce this regularizer, strongly convex risk, or a strictly convex regularizer here with some parameter epsilon that captures the agent's degree of bounded rationality, right? So we've transformed the game, we've introduced risk, and we've introduced bounded rationality. Risk through this risk metric rho, and bounded rationality through this regularizer and this parameter epsilon. And now again, we can kind of talk about the natural solution concept in this type of game. And the natural solution concept now for risk-averse and individually boundedly rational agents is going to be what we call a risk-averse quantal response equilibrium. And again, this is going to be an equilibrium where no player has an incentive to unilaterally deviate, in the space of quantal responses. So given these definitions, what we're actually going to show is that a class of these RQE is computationally tractable in all games. And I'll focus on two players for today, but the paper has the results for the n player case. So the key to our argument is what's known as a dual representation theorem for risk, which basically says that we can write any risk metric rho as, as in this kind of variational form as the max over some probability distribution P and some metric D around pi minus I. And we introduce this new parameter here, tau, which basically determines the agent's degree of risk aversion, right? So risk can basically be fully captured by a penalty function D that's convex in the first argument. So for example, when D is the KL divergence, we can recover something like the KL, the entropic risk. And tau here captures the agent's degree of risk aversion. When tau goes to 0, you get risk neutral games. And when tau goes to infinity, you recover basically a security strategy of the player. So the player kind of starts playing a zero-sum game and disregarding entirely what the opponent is actually doing. Great. So the interpretation for this, at least the intuition, is that with this dual representation theorem, we could kind of introduce a fake adversary for each player, which is fully adversarial, but is kind of penalized for deviations from the opponent's real strategy. And this interpretation is really important for our proof later on. But this basically lets us prove this result here, which is that if the bounded rationality and risk aversion parameters of player 1 are greater, the product of them is greater than the product of those for player 2, or the converse, then a resulting RQE can be computed using no regret learning on a related 4-player convex game. So kind of this is a nice result. This result, what's kind of remarkable about it to me is that it doesn't depend on the structure of the underlying game at all. So it will hold for all general sum games. And it only really depends on players' relative degrees of risk aversion and bounded rationality, right? So this is kind of, and you immediately get, because of this result on no regret learning, you could use any no regret learning algorithm to, compute these equilibria in a decentralized way. And so just to give you, this is my visualization of this theorem. So, this region here in blue is the set of all RQE that are computationally tractable. So if you were just to, choose a point in this blue regime, that would give rise to an equilibrium across all games. And that equilibrium could be computed using no regret learning. It kind of makes intuitive sense that this regime here at 0, 0 is not in this blue regime, because this is exactly the regime of Nash equilibria, which we know is computationally intractable. So there is a gap here between Nash and what we can compute. And there's something interesting that also happens, at infinity here, because at infinity, each player is so risk averse that they treat their opponent as adversarial. And so that makes them basically just solve a zero-sum game. And we know that a zero-sum game is computationally tractable for any, amount of bounded rationality that you might add. And so we kind of, this class of RQE nicely interpolates between our existing results on zero-sum games and existing results on Nash equilibria in a very kind of clean way, which is why I find it kind of very nice. Great. So any questions about this result so far? Cool. If not, I'll kind of just walk you through the proof at a very high level. And so we basically just start with the 2-player game, which I've written in this kind of condensed form here. We write this through the dual representation theorem as this min-max of this penalty function and this bounded rationality parameter, and exactly in how I showed it before. And then we basically lift this game to a 4-player game. So we introduce 2 new players, these P1 and this P2, that also would like to minimize the negative of all of these functions. So what's nice is if you actually look at this 4-player game, it's a 4-player zero-sum game. And that's kind of very powerful because using the convexity and concavity of the game and all of these functions, you can actually show that the CCE for this game will always coincide with the Nash equilibria of the smaller game. And that this result is kind of independent of both of these kind of reward functions, R1 and R2. And so, that's kind of the proof at a very high level. It's a little bit more technical, but just to give you some intuition, we essentially just lift the game to a 4-player game and analyze it there where there's some really nice structure that we can exploit. So, this kind of in the end, we end up with this theorem that basically says that we have a class of equilibria that's independent of the reward structure. So it applies to all games that's computationally tractable. And kind of crucially, it arises only due to the combination of risk aversion and bounded rationality. And we could kind of extend these results to n-player games and dynamic games or finite horizon dynamic games just through dynamic programming. So that's kind of gives us a nice kind of basis to start building algorithms off of for reinforcement learning. So I'll kind of, maybe before I kind of present some results on dynamic games, I want to kind of convince you that this class of RQE is expressive in some sense, and that this restriction on computational tractability captures some interesting behaviors that we might actually want to get. So to do this, we dived into the literature in behavioral economics, and we looked at kind of 2 papers where they actually had and reported their data on, they had people play a kind of a set of 2-player games over and over again until they converge. And then they basically just saw how they computed the, several other equilibrium concepts associated with that game, and they wanted to see which equilibrium concepts match human play. So we took kind of all of the same data from these kind of classic papers in behavioral economics. And we kind of just tried to recreate human play with our RQE notion. And so, I'm just showing you here, this is the payoff for the games, game 4 from this player, game A, game B, game C. And then this is, another game where they again show the aggregate, play of a bunch of people along with the actual equilibria of the game. And so what we're able to show is that, for each of those games, we can actually show that there exists an RQE that can recreate people's aggregate play to within 3 decimal places. And this is kind of independent of the risk metric and the class of bounded rationality that you choose. So these are kind of our results. I'm showing here the same regime as before, and then each of these markers is just basically showing you the parameters needed to recreate human play in that game. And so basically in all of these games, we can recreate human play using RQE. So at least to me, that hints that this class is maybe expressive enough to be useful. And so that was kind of nice. Any questions about that? Great. So, in the kind of remainder of this part of the talk, we basically just extend those results to finite horizon risk-averse Markov games. So now we just introduce some kind of dynamics into the problem. So, players now would like to maximize their utility over finite horizon H. They have finite action spaces, but now there's a finite state space as well. And there's dynamics, which determine, how the environment moves from state S at time t to state S prime at time t+1, given the actions of all the players. Right, so this is kind of your classical setup of multi-agent reinforcement learning in a finite horizon sense. And so now we're also going to assume that people could be risk averse also just to the randomness in the environment. And we're just going to assume that we have access to a generative model. So we can collect IID samples of the transitions and the rewards to estimate R and P. This basically is just a simplifying assumption, just so that we can start to understand the sample complexity of this problem. It means that we're not actually ever doing a reinforcement learning algorithm on this problem, but it just helps us understand some of the theoretical properties of RQE a little bit better. But then what we can actually show is that we can approximate a Markov RQE in polynomial time. And we don't actually, because of the no regret structure that in our solvers, we don't actually pay a multiplicative dependence on the size of the action spaces. So we don't suffer from what's known as the curse of multi-agency in multi-agent reinforcement learning. So the curse of multi-agency is when you pay the product here of all the size of the action spaces, and we pay the sum. And so this is kind of a very desired property. But rather than linger too long on this slide, I want to show you some kind of experiments that in a very toy setting that we ran. So this is a very kind of simple grid world experiment. We're going to start where there's going to be two agents, a red and a blue. The red agent is going to start and try to go to this red square here. The blue agent would like to go to this blue square over here, where they'll collect, high reward. If they fall into any of the black squares, they'll be stuck there for all time and get a really negative reward. So that's something that they really don't want to happen. But the closer the two agents get to each other, the more randomness there will be in their transitions. So they'll have kind of less ability to successfully complete, move in the direction that they'd like. So we're starting on the right over here. So this first case is the case where red is more risk averse and blue is less risk averse. Oh, sorry, let me go back. And in this setting, what you'll see is that the red agents kind of, would like to get to the red, but they wait in this bottom corner here where it's very safe before and allow blue to progress to the goal. And then red, will kind of finalize we'll go to the goal. So we can play it again here. Red waits for blue to pass, and then blue will go to the goal. And then red will kind of continue on to the goal. And this makes sense because red is more risk averse. They don't want to take the risk of colliding with blue in this state, which might send them into these black states with higher probability. And then blue is slightly more risk averse, so it'll be the one that goes first. If we make red less risk averse, we can see that the equilibrium completely changes. If we make blue more risk averse, the equilibrium completely changes. And you'll basically see that the blue agent just hides in the corner here instead of finishing the goal because they're so risk averse that it's actually better for them to stay here than even risk getting anywhere close to these black states. And in this case, the equilibrium changes and the red will actually just go to their goal. So I think what's nice about these experiments is that all we're doing is changing the risk aversion parameters, and what you see is that you get some nice kind of intuitive behaviors that come out of this. And furthermore, we can actually compute these solutions, and we have guarantees that we can compute these solutions in a way that we don't have for any other multi-agent reinforcement learning algorithm. Great. So that kind of finishes just this first part of the talk. And to me, the takeaway is that by giving RL agents kind of more human-like behaviors or more human-like features, we can get an expressive class of computationally tractable in all finite horizon Markov games. So we've only really scratched the surface here. I think that there's still lots of open questions on extending this to infinite horizon problems, actually coming up with reinforcement learning algorithms and coming up with scalable RL algorithms and demos. But I'm excited by some of these ideas. So in the second part of the talk, I'll move on to thinking about distribution shift and kind of some new models of distribution shift. And this is joint work with my student Lauren Conger at Caltech, my colleague Franca Hoffman in applied math at Caltech, and Lily Ratliff, who's a collaborator at UW. So basically, the motivation for this line of work is that distribution shifts is to deal with distribution shifts. Now, I'd say in a lot of machine learning problems, distribution shifts are considered to be exogenous to the learning problems, meaning that the fact that you're deploying a learning algorithm or that you're using these learning algorithms for decision making is assumed to not affect the distribution shift. Right? This might make sense. For example, the distribution changing as you go from city to city, for a self-driving car makes sense. The fact that you're using self-driving cars won't really change the weather in cities. In hospitals also, the fact that you're using scans or that you're reading scans, it doesn't really change the fact that distribution shift occurs and so on. But I'd say that in a lot of many real world scenarios, the distribution shifts actually arise in response to the use of a learning algorithm. And in fact, there's oftentimes some kind of strategic component to the use of a learning algorithm. And so, maybe in an extreme case, this is maybe a little bit of a toy case, but never probably in no data point in the training set for cruise did they ever have someone putting a cone on the hood of their car to stop the car from moving. But as soon as you start deploying cruise cars in San Francisco, this is something that happens, and this is totally out. Your distribution just changes. And there's evidence here from Twitter as well, that the fact that Twitter algorithms, or X, I should say, the fact that X algorithms, promote tweets based off of retweets, have made people, instead of retweeting, just post pictures of tweets, so that people wouldn't get credit for retweeting, and so on. And so just the fact that you're using, features of and algorithmically changes the distribution of the data that it's trained on. So, our goal was to design a simple model of distribution shift that captures both these exogenous shifts and these endogenous sources of distribution shift. And so just a toy model here where we have a decision maker who deploys a model X. Strategic agents are just going to respond with strategic data from a distribution rho. And rho is going to evolve over time in response to X. So what's nice is we can actually just write down a PDE for this. So we can write down basically a PDE, which basically describes how the distribution of data will evolve over time. And this is basically just, it depends on some kind of potential function, which captures the endogenous shift, as basically people wanting to minimize some function V that depends on the deployed model X. And there's this cost of changing data here, which also helps you regularize, which also can be thought of as Brownian motion or some kind of endogenous shift as well. So, this really simple model already helps us model real world shifts. So, what I'm going to show you here is just an attempt to recreate this kind of real world shift that we saw earlier on in the talk. With this very simple model. So all we do is assume that V is a logistic loss, and I'll just play this video here. And what you'll see is that this really simple model already captures this kind of thresholding phenomenon. So when our population is made up of strategic agents who'd like to get on the other side of the boundary, just maximize their classification accuracy, that's enough to give rise to this really simple form of distribution shift that we see. But I also want to point out that this is actually a very kind of complicated behavior because in some sense it's discontinuous. And this is a form of distribution shift that couldn't be captured, using adversarial robustness or normal forms of dealing with distribution shift. And so, and it captures the ground truth very well. So, this on the right here, I'm just showing you the ground truth and what we're able to simulate, and they match up almost perfectly. So,
Eric, there is a question from Grant, how to actually find the potential function?
Yeah, that's a very good question. So that's something that we're actively working on at the moment. So in this first example, we kind of just did it by inspection. So we just basically said this potential function should be a logistic loss because this is a binary classification problem. And so it should just kind of, and so we ran it with this, and we got the desired behavior. But I think that is a very good question. How, like, learning these potential functions from data, I think is an exciting and relevant problem. But this is kind of more of a modeling exercise at the moment. So what's nice is that we can actually add more things to this problem. So we can also use, the first model was maybe very simple, but it captured some realistic behaviors. We can also add kind of other features. So we can add this, what we call this non-local interaction kernel W here, which captures interactions within the population itself. So this captures the idea that similar individuals might interact with each other, might influence each other, and things like this. And this might also be a driving force in the distribution. I should mention that these types of dynamics have been looked at in biology a lot for modeling insect swarms and things like this, but we find that it could also be useful for modeling, people's decisions and opinion dynamics and things like this. And so I'll just give you a couple of examples. So this is what happens if this kernel here has this form here. So this kind of, inverted, this inverted shape. This is what's known as a consensus kernel. It kind of drives people who are close together, kind of closer together. And so on the right here, I'm just showing you what would happen if we don't have a V, and this is just the effect of the consensus kernel. And so you can see that it kind of drives the distribution closer to itself, kind of concentrates the distribution. You could also introduce things like this attractive repulsive kernel here. This might be a good, there's evidence in social networks that, for example, you are, very attracted to people close by to you and very repulsed by people far away from you. And so, sorry, if this gives rise to this type of distribution over here. So you can kind of add all of these features into these dynamics. And then you could also start to ask, what happens if you retrain the model, right? If you're trying to keep up with distribution shift. And so we can actually just, look at, add the dynamics of a retrained machine learning algorithm, next to our population dynamics and see what happens out of this. And so, by lifting this machine learning thing into infinite dimensions, we get these kind of coupled Wasserstein gradient flows here, where one player would like to minimize one function, the other one is trying to minimize the other, but they're coupled. And we can basically just, simulate these dynamics. And so on the right here, I'm just showing you, again, a very simple picture where we have two distributions. The orange distribution is fixed. The blue distribution is strategic and would like to get on the right side of this classifier in black. And the classifier is constantly being retrained to try and maximize its classification or accuracy. And what you can see is that just the coupled dynamics, the fact that you're doing this retraining can basically split this blue distribution and give rise to something that kind of looks like some form of polarization, right? Some kind of multimodal distribution here. But we can even go further. We can actually think about, how is retraining as good as basically no retraining and just kind of fixing your classifier to something suboptimal. And what's interesting just by running these experiments is you can see that retraining could actually give you worse equilibrium performance than just, initializing your classifier suboptimally and then not retraining at all. That's because at equilibrium, fewer people will actually try and, get to the right side of the boundary. And so your classification accuracy is actually better at equilibrium. And then you could actually think about what happens if you try and be extra smart and try and, model distribution shift and take it into account. So this is some kind of exciting or something that I thought was kind of cute, which is on the right, we basically show the outcome, what happens if you take into account the fact that there is a distribution shift, but you model the distribution shift just as a shift in the mean of the distribution. And you try and retrain according to that. What you end up with is this classifier here. And actually you get to a much worse result than just naive retraining. And so what I like about this example is that it shows that if you use a very simple model of distribution shift, you could actually end up even worse than doing kind of not taking into account distribution shift at all. And so you have to be very careful how you model this. So, just to wrap up, we can actually do some theory to understand this model as well. These types of kind of coupled Wasserstein gradient flows have been looked at in applied math and biology and game theory. There's not really any good convergence guarantees, I would say, under kind of more general conditions. And so working with some of my colleagues in applied math, we're able to give kind of the existence of steady states and convergence guarantees and rates in zero-sum games, and existence of steady states and convergence under kind of more generalized conditions. Some of these results actually solve an open problem from the conference on learning theory last year, but I won't go into detail there. But the takeaway to me is just that, we've come up with these kind of new kind of PDE models of distribution shift. that we can that are actually maybe useful and give us insights into how we might deal with dynamic distribution shifts. We have ongoing work here with coming up with like good simulators and generative models for scaling these things. And along the way, we have some exciting kind of connections with score-based generative modeling that I'm happy to talk about later on. But that kind of ends the talk. So, I kind of gave you a small vignette of two different lines of work, which I think are really coming from this idea of bringing strategic or really designing learning algorithms from the ground up for strategic environments. And so, to me, the takeaway is that economics can give you new algorithmic ideas and give you new understanding of how machine learning algorithms should work in the real world. But we've only really scratched the surface. So with that, I'll take questions. Thanks for listening.
Okay, thank you so much for your great talk. And Jared has he went to a faculty meeting, so he asked me to host the Q&A session. And thank you
No
so much
problem.
again for your like very insightful and interesting talk. Okay, so any
Thank
questions? You can post the questions in the like chat or just ask the questions. Oh, so it seems that your like talk is super clear, so everybody like understand all the stuff. Yeah.
Sorry.
Oh,
Oh,
there's one question.
Can I ask a question?
yeah, of course.
Thank you very much for your very good delivery of your presentation, and I was really get new insights. I'm like not a, I don't know, I can't say myself like an IT guy about machine learning. I'm a PhD student, and I'm working on the topic related to the financial inclusion and the well-being. Your topic was very interesting, and it's more about the behavioral economics, because I think it may be quantifiable with some kind of data. I think that you can retrieve the data through the machine learning. My question is, do you have any idea how to integrate the financial inclusion or well-being? Did you come across with like applying the machine learning instruments to these kind of topics?
Yeah, we haven't really applied any of our stuff to kind of finance, but I would say that the convex risk metrics that we take into account in that first part of the talk, a lot of that is actually coming from mathematical finance. So actually the structure of those convex risk metrics are things that have been very well studied in mathematical finance, and we just use them to capture this idea of risk in a kind of nice mathematically clean form that allows us to get our later results. So I think there must be links. I think we haven't explored them very much yet.
So the last question is, to retrieve the data, how you are retrieving the data, or the AI itself, it's like collecting the data through the network?
Yeah, so our goal is to go more towards reinforcement learning, where the agents themselves will kind of over time collect data on their rewards, and then you would learn to play these types of equilibria over time.
Thank you so much. Thank you.
Thank you. There's a question here, which is, for coupled gradient scores, would it be possible that we encounter multiple equilibria and steady state solutions? Also, what will be the convergence rate? Yeah. So in the coupled gradient flow setting, we look at the settings that we look at are basically settings in which or at least from a theoretical standpoint, are settings in which you have kind of enough structure that you have kind of uniqueness of the equilibria, and then you can get rates. I think if you have multiple equilibria or steady states, I think that's a very hard problem. And it seems very hard to address in some sense. So, I think in theory, there's probably not much we can say. In practice, we can see that, this model, does pretty well, but we can't have any guarantees on which equilibria it'll converge to or anything like that.
So are there any other questions? Okay, so we have already run out of time. So thank you so much, Eric, for your like great talk. It's super insightful and it's very interesting. Yeah, many
Thank you.
questions that yeah. Thank
Thanks.
you,
Happy
thank
to chat.
you,
See you. Bye.
and to see you.